We're now ready for problem 14. They give us a function, y equals f of x equals 6x minus 1, x equals 4, and delta x equals 4. So this is a problem where we learned about what I call differentials and margins or marginals. Some pretty unique and different kind of stuff. So I asked for 3 questions. Maybe I can work out the problem right here. If you watched my lecture on this, I ended up doing what I called actual calculations and estimate. An actual equation is part A, it's asking for delta y. Delta y is the function at x plus delta x minus the function at x. So basically it's saying if x is changed by delta x, how much does y change? Once again, don't have time to explain all this. If you don't understand this, please go back and watch my lecture on it. So in this case, x plus delta x, this problem's a little strange because they define x to be 4 and delta x to be 4. Usually delta x is a lot smaller, but it is what it is. So basically we're looking at the function of 4 plus 4, which is really the function when we plug an 8 in. So here's the function 6x minus 1. 48 minus 1 is 47. F of x is just f of 4. So we plug in 4 into our function. 6 times 4 minus 1. 24 minus 1, 23. So therefore, you subtract f of x plus delta x, which is 47, minus f of x, which is 23, end up with 24. Now, when you look at these problems, sometimes it's not quite clear because the second part, I started out, I wanted to actually calculate dy, but here they actually want an equation. So now this dy, this is like the equation for what I call the estimate. So they're saying dy is the first derivative of the function dx. So what they want you to put in here is they want you to go take the first derivative of the function. Well, the first derivative of the function is pretty straightforward. The first derivative of 6x minus 1 is just 6. So even though it's a number, this is really the first derivative of the function. And then they say for this part, now go ahead and perform this calculation. So dy, just to make it clear, this isn't the best problem to use to explain things. If the function is 6x minus 1, the first derivative is just 6. So this is the first derivative. Now they want you to do the calculation. So the dx in this case, the delta x becomes the dx. So this is really going to be 6 times 4. So the dy equals 24. All right. Once again, I'm not going to take time to explain all this. You can go back and watch the lecture if you forget how to do those kinds of problems. All right, number 15. 15 is another problem about using margins or marginal kinds of calculations, except it's a story problem. So they're looking at revenue, how much money a company makes. In this case, looks like they're selling lawn chairs. Here's an equation for the revenue. And currently they sell 70 lawn chairs daily. First question, what's the current daily revenue? Well, this is the equation for the revenue. Since they sell 70 per day, you plug in 70 for X here. Pretty straightforward. .006 times 70 cubed plus 0.03 times 70 squared plus 0.7 times 70. So this is obviously basically a calculator problem, this first one. So when you grab your calculator and you crunch all the numbers, you get $2,254. So that's how much they're making every day when they sell 70 chairs. How much would the revenue increase if 73 lawn chairs were sold each day? So what I'm going to do is, now I'm going to say, well, what happens when I sell 73 lawn chairs? So you go back to the same equation, and now I'm going to plug in 73 for X plus 0.03 times 73 squared plus 0.7 times 73. And when you do that, you get sort of a pain, but eventually in this case you get 2545.07. So now that's how much revenue when they sell 73 chairs. Now the question is, how much would the revenue increase? So really what you have to do is you have to take the amount they make selling 73 chairs, and then you subtract the amount they make selling 70 chairs. So it's really 2545.07. So for part B, the answer is really 2545.07 minus 2254. That ends up being $291.07. So that's how much the revenue increases if they happen to sell 3 shares more per day. Now, here's how I did the marginal revenue. The marginal revenue we learned is simply the derivative of the revenue. Once again, no time not to explain it. You can go back and watch the video. So the derivative of the revenue, so here's the equation. So you got to take the derivative of these 3 terms. So 3 times 0.006, 0.018 x squared plus 0.06 x plus 0.7. And now we want to calculate that when x is 70. So plug in 70 in here for x. And when you do that, you get $93.10. So in a sense, this is an estimate of how much money you make per day for each extra lawn chair you sell. You're at 70. If you sell 1 more lawn chair, this is how much more you make. And then in part D, that's what they ask. They say use the answer for C to estimate. Once again, look at the word estimate. The revenue is 71 chairs, 72 chairs, 73 chairs. This is how much is made per chair. So for 71 chairs, you take the revenue and you add 90, so you take the 2254. So for this one, 2254 plus, because this is the amount of revenue for 70 chairs, and this is how much is added on for the 1 chair. So 2254 plus 93.1, 2347.1. Now, what happens if you bump it up 2 chairs? Well, you still start at 70 chairs, but since you bump it up 2 chairs, 93.10 is how much extra you make per chair. So if it's 2 chairs, you take 2 times 93.10 and add that to 2254. And when you do that, you get 2440 plus 20. And then likewise, the estimate of the revenue from 73 chairs is 2533.3. All right, so another problem, we talk about marginal, in this case, revenue. If you've already forgotten about this stuff, go back and review the video and do some sample problems. All right, now here's one problem on something that was a little bit different that you may have already forgotten by now. Called elasticity. Where elasticity is calculation that sort of helps you to set the price of a product so you can make the maximum money. Once again, I covered in detail what elasticity is and Now I will go ahead and write the equation for elasticity because we're going to use it. And I did it in terms of the price. So the elasticity as a function of price is a negative the price of the product times the first derivative of the demand function over the demand function, and both the first derivative and the function, demand function, are both evaluated at the price you're trying to calculate the elasticity for. So here, this first part A, they're looking for the equation. So I plug things in here. So here's my demand function, 358 minus P. The key thing I'm going to have to calculate is the first derivative, which in this case is very straightforward. It's just minus 1. So now I simply got the negative. I got P times the first derivative, which is -1, all over the demand function, which is 358 minus P. If I cancel out these minus signs, it turns out the elasticity is going to be P over 358 minus P. So now part B, find elasticity at the given price. And the price we're looking at is 104. So basically plug in 104. So the elasticity at 104 is going to be 104 over 358 minus 104. Notice integer or fraction, so we're not gonna make this a decimal. Gonna have to see if this fraction reduces. So this should be 254. So if I start reducing, I know I can at least divide by 2. 52 over 1. And I don't think it's going to reduce anymore. So it's sort of an ugly fraction, but basically the elasticity is 52 over 127. And then they say, so now for a price of 104, is the elasticity is elastic, inelastic, or in unit? Unit elasticity means it equals 1. And the way this works is if it's less than 1, inelastic is when the elasticity is less than 1. Elastic is greater than 1. So this is obviously less than 1. So that number is what we call inelastic. Now to find the maximum, basically, the maximum price you'd set to make the maximum amount of money, or the price you would set to make the maximum amount of revenue, is you want the elasticity equal 1. So you just take your elasticity equation and you set it equal to 1, and you solve for P. So in this case, I'll divide both sides by this denominator. I'll add P to both sides. Divide both sides by 2. Now, if I did this in my head, I think it's 178, but I better confirm that. Oh, see, I was off, 179. So maximum revenue is achieved when we charge 179. All right. Now earlier, I talked about implicit differentiation. I sort of jumped the gun. Now we are finally here where number 17, we are going to do implicit differentiation. So that's where we're going to find the derivative, but as it turns out, we aren't really going to try and get the y by itself. We're just going to take the derivative of both sides. So if you recall, once again, I'm not really taking time to explain things as much as just work them out. My goal is to find dy dx. I take the derivative of both sides of the equation with respect to x. So the derivative of 3xy, first of all, the 3 comes out front. Now the x and y are both variables, so you have to use the product rule. But the key thing is, what am I taking the derivative with respect to? In this case, it's x. So it's going to affect what my answers are going to be when I do this. So the product rule says the first times the derivative of the second. Well, the derivative of y as a variable is just 1. But because y is different than this dx, I have to tack on the dy dx. So this is the first half of the product rule. The first times the derivative of the second plus the second times the derivative of the first. Derivative of x as a variable is just 1. And because x is the same as the dx, I'm done here. So derivative of 3xy is this. Derivative of x is just going to be 0. Derivative of 0 is 0. So this whole thing equals 0. Actually, I can divide both sides by 3, and it sort of goes away. So when it's all said and done, I have x times dy dx plus y equals 0. Now, if I want to solve for dy dx, subtract y from both sides. If I divide both sides by x, then I get my answer, dy dx equals negative y over x. And that is, in fact, the correct answer. All right, so hopefully you remember how to do this implicit differentiation. So number 18, got a little twist to it. It is an implicit differentiation problem, but actually, after we find the derivative, it wants us to find the slope of the curve at the point. Two-part problem. So let's just first find dy dx, and then we'll worry about the second part. So my equation is y squared minus x cubed equals 28. So I'm going to have to, in order to find the derivative or find dy dx, I'm going to have to use implicit differentiation. So I take the derivative of both sides with respect to x. So here, derivative of y squared is just 2y, but because my variable here, y, is different than the variable down here, x, I have to tack on the y dx. So derivative of y squared is this, minus derivative of x cubed is 3x squared. Since my variable x here is the same as the variable down here, I don't have to add anything else on. So it's just 3x squared. On the right side of the equation, the derivative of a constant is just 0. So now I need to just solve for the y dx. Let me add 3x to both sides. Or 3x squared to both sides. Then divide both sides by 2y. So there is my derivative. Make sure I got the correct answer before I keep going. Yep, 3x squared over 2y. The slope of the graph at the given point is all right. So we've done this before, but it's been a while. So this is the idea where they give you a point. So here's x and y. They want you to find the slope at that point. Well, the slope is another word for the derivative, right? Let me write it like this. What they really want is the derivative at the point 2 minus 6. Well, I just found dy dx to be 3x squared over 2y. So I plug in 2 for x, negative 6 for y. Four times 3 is 12. Negative 6 times 2 is negative 12. If I didn't mess up, it looks like the slope at that point is negative 1. All right, some more implicit differentiation. Now here's a little twist in that here's your equation, y equals x squared plus 5. And now you can see here, they're wanting dy dt. T is normally thought of as time. So this is where we're actually taking derivative with respect to time, a third variable. But it's not that hard. So they're wanting dy dt. So what you do is you take your original equation, y equals, I'm going to take derivative of both sides of this equation with respect to time. And what's going to be interesting is it doesn't matter whether I'm looking at y or x. None of the variables in the equation are the same as what I'm taking the variable with respect to. So I'm going to have to always tack on the extra stuff. So the derivative of y is just 1, but because the variables are different, I tack on the dy dt. Derivative of x squared is just 2x, but because my variable here is x, down here it's t, I have to tack on dx dt, and the derivative of 5 is just 0. So if I clean this up a little bit, I could basically say dy dt equals 2x times dx dt. And what they've asked me to do is, first of all, they told me up here dx dt is 3 when x is 4. And then they say, so find dy dt when x is 4. Here's an equation for dy dt. X is 4, dx dt is 3. So I can plug those in, plug in 4 for x, plug in 3 for dx dt. And you get 24. Not too bad. That's it. Now we're going to do the same kind of thing. These are called related rates, where we're looking at something as it changes in time. Something's increasing or decreasing. Sort of like a story problem. So number 20, a circle is growing. Its radius increasing by 4 millimeters per second. Find the rate at which the area is changing at the moment when the radius is 25. So we're talking about a circle, right? So this is where you have to remember your geometry. Circle has a radius r, right? This is from the center to the edge of the circle. And in geometry, we learned an equation for the area of the circle is pi r squared, where pi is that special number 3.1415, whatever. So this is how you calculate the area of a circle, but the size of the circle, it keeps changing, it's increasing. So it changes with time. So what we have to do is, so here's the equation for the area, but I've got to take the derivative of both sides with respect to time. Since the area is always changing, I have to now, in a sense, take this area equation and add in the time element. And the way I do that is I take the derivative of both sides with respect to time. So this becomes sort of implicit differentiation. Derivative of A is just 1. And since A is different than T, we have the dA dt. On the right-hand side, pi is just a constant, it's a number. So it tags along. The derivative of r squared is just 2r. And since r is different than t, then you tack on the dr dt. So if I sort of clean this up a little bit, basically this is saying, now this dA dt, we call that the rate at which the area is changing. How fast is the area changing? It could either be increasing or decreasing. And it equals 2 pi, these are both constants, times the radius times dr dt. So when you do a calculation for this one, it's like a snapshot in time. It's like a freeze frame. If they want you to actually do a calculation, or you have to stop at a certain moment in time and plug information in and do a calculation. And that's what they're doing here. Because they say a circle is growing, its radius increasing by 4 millimeters per second. Radius increasing, so they've told us the RDT is the rate that the radius is changing, either growing, increasing, or decreasing. They told us it's 4 millimeters per second. So the RDT is 4. And they say when the radius is 25, so that's the snapshot in time. The circle is constantly growing, but at the moment in time, which we're going to sort of inspect it, it's when, for our snapshot, we want to stop and look at it when the radius is 25. And what they're asking for is, how is the area changing? That is the ADT, the rate that the area is changing. So basically, we want to know the ADT when the radius is 25 and knowing that the radius is changing at 4 millimeters per second. So we basically have everything we need to plug in to this. So 2 times pi times the radius is 25 times the RDT is 4. So this one, we're going to grab our calculator. They want us to round it to the nearest thousandth. So this is where it's important. Hopefully you have a pi key on your calculator. You need to enter the pi key. You can't just enter 3.14, or your answer won't be quite right. So 2, so you can see here, I entered 2 times, I have a pi key here. Because when I enter pi, it enters the whole number, which is what I need, times 25 times 4. So the thousandth place is the 3 digits. So 628.318, since this is a 5, this bumps up to 9. 628.319. And the units, since it's area, this area is changing, area is square millimeters per second. All right, so that's called a related rate problem, where you have different rates. In this case, the rate of the area and the rate of the radius. You got different things always changing. Matter of fact, here's another related rate problem. Number 21. Another like story problem. In a trend that scientists attribute, at least in part, to global warming, a certain floating cap of sea ice has been shrinking since 1980. The ice cap always shrinks in the summer and grows in the winter. Average minimum size of the ice cap in square miles can be approximated by A equals pi r squared. In 2013, the radius of the ice cap was approximately 773 miles and was shrinking at a rate of approximately 4.2 miles per year. How fast was the area changing at that time? So once again, and then here they want you to give the units, but let me just work out the problem. So here is the equation it's based off of. The area of this ice cap is pi r squared. So the area is changing and the radius is constantly changing in time. And they're wanting to eventually, well, let's just do this. Let's convert this. Let's add the time element. We always do that by taking the derivative of both sides with respect to time. So the left side is going to be dA dt. Now the pi is a constant. Derivative of r squared is just 2r. But then we have to tack on the dr dt. So now this is an equation that describes how things are changing. Here, this is the rate the area is changing. Here's the rate that the radius is changing. And we also have to plug in the actual value of the radius at the point in time at which we're looking at it. So now they say 2013, the radius of the ice cap was approximately 773 miles. So here's the point in time we're looking at. The radius is 773 miles. And we're shrinking at a rate of approximately 4.2 miles per year. So the radius is shrinking. Shrinking means it's decreasing. So that means a negative rate. Then they say, how fast was the area changing? So really then what they're asking is, they want us to calculate dA dt. If you look at this equation, pi is a number, 2 times r, they gave us the r, times the dr dt, they've given us the dr dt. So I just need to plug everything in. And then grab my calculator. So pi times 2 times r, which is 773, times dr dt, which is negative 4.2. So now here they say round to the nearest integer. So it's sort of crazy. The problem before they wanted to the 1,000. Here they just want like a whole number. So anyways, pi times 2 times 773 times 4.2 negative. So it looks like negative 20,398.98. So I think it's negative 20,399. And the units, once again, since it's an area change in the area, it's going to be in square miles per year. Square miles per year, I guess, would have been. Are these my choices? I don't even see the correct answer. Maybe it printed it out incorrectly. I think this printing, I don't know what's going on here, but the thing must have gotten messed up printed out. I know the units are definitely square miles per year. All right, another related rate problem. All right, the next problem, actually, we start doing integration. So now is a good time to stop this video, and the next video we will start working out problems involving integration.